Okay, welcome back to the stream. I'm getting an error message. Can you hear me? I'm talking. Do we have audio? Okay. I don't know what the issue was. Okay. So welcome back to the stream. The plan for today is to add types to our more types to our C interpreter. So currently the only real type that we support is int, and then functions that take and return it. And the goal is to extend those to first we add void, which is probably going to be quite easy to add, and then to all the other types, to more integer types. So I did a stream last week, but it ran into technical difficulties, so I never published the video. There I mostly just did some refactoring in preparation for the ACE stream. Previously, the types were children of the AST, but now the types are separate entities, and they are also all unique. Unique and interned. The types are now interned, so we only have one type, one instance of built-in type that represent ints. So this is just a technical refactoring that made it a bit easier. So what we're going to do now is add more types, and we'll start by adding void. So void is a built-in type. So let's add it here, compile, and follow the errors. And then we also need to print it. Okay. Okay. Then when we pass a type specifier, we also want to pass void. So we are having int, and we are also now having void. So int and void. So now we are passing void, and we're also creating it. This compiles, but of course, when we try and actually use it, so void can be used as a return type for a function. So I can do void f, which does, let's say, this print, and then we're calling f. The AST looks good, so we've got a function decor that returns void and calls the function and so on. So that is all good. But of course, the bytecode that we generate is wrong. So we generate a function that still returns a value because we're currently hard-coding it, and then we're also generating a synthetic return statement for that. So let's change the codegen. When we create a function, codegen function, right here we're saying that it always returns one value. But of course, if the return type is void, then it does not return a value, it does not return anything. So let's see whether the return type is void I believe the easiest way to do is to add like a bunch of functions for types. So like type queries is void. And if the type is void, so if we can cast it to a built-in type, then the built-in type kind should be void. Otherwise, return false. And so, okay. And then during codegen, we can then ask if the return type of the function, we don't have an easy way to get the return type, so let's add an easy way to get the return type. So the return type, for that we get the type, downcast it to a function type, because we know that the type of a function is always a function. And then we can get its return type. Actually, I believe it's better if we override type, so it returns a function type. Yeah, I believe that is nicer. And then we call the version of the base class and then simply downcast it. And so here I can say decal type. Now I can get the return type. And if this is void, then we return no values, otherwise we return 1. And we want U and ATs here. Okay. This will then create an assertion failure, because we're still having a return, generating an implicit return here at the very end. So let's refactor this out. So return count 0, 1. And here we are passing the return count. Then at the very end, we add an implicit return if we're not returning what. Okay. So we always need to generate a return statement, but we only... Okay, so like that. So we always generate a return statement, but only if we actually need a value do we push a value. Okay, now I'm getting an invalid function. What? That is a strange error. I believe I know. So we're getting an error because we are so somewhere we're pushing the address of a function. Yeah, pushing the address of a function onto the stack. No, that is correct. So there's some point where we're hard coding the signature of the function, but we shouldn't do that. So where do we keeping track of all the functions here? Where do we? No, that seems correct. So let me see what happens when we call a void function. So we are calling the function. What is its signature? Yeah, it's 1. Wait, why is it 1, 1? Oh, it's probably void, right? We are probably calling the fib function. So we're calling the flip function, which has a signature of 1, 1, and that is correct. Calling the flip function, which has a signature of 1, 1, that is also correct. I mean, we already knew that. Still calling the flip function. Now we're calling f. What is f's signature? It's 0, 0. So that should be correct. So we're pushing a function address of a 0, 0 function onto the stack in order to call it. So this happens here. But, so when we do a call indirect, right here. So when we do an indirect call, we're still hard coding that it returns 1 value, but it doesn't actually return 1 value. So, same deal. So how do we get the return type? We get the type. So the type of the function, which is a function type. So we can downcast this one to the function type. And then I can get the return type and the argument count. So I don't need to count them here in the loop. Instead I can do argument count. What's it called? What are you complaining about? Oh, typo here. Okay, so the argument count. These are the parameters. How many parameters we have? Okay, and then the return count is we query whether the return type is void. If it is, then we return 0, otherwise we return 1 value. Now let's do that right here. Okay, so the argument count, and then instead of hard coding 1, we use our newly computed return count. Okay, and now we are calling our main function, calls f, but it does not expect it to return a value, and this still works. Okay, so we've now are able to use void as a return type, but there are many things that we still need to check for. Right, so this is the code that is needed to support the happy path. But the majority of a compiler's job is to generate error messages for like things you can do that aren't allowed. So let's add a bunch of error messages. So for example, what isn't allowed, something like this. Instead, what happens is we get like a cryptic assertion failure when we do code gen. Because we generate a return statement for the function, but it does not, like the signature does not match the computed output count. So we need to catch that one earlier. So when we do a return statement, we need to check whether the current function, the expression of the return statement, its type needs to match the return type of the current function. So first thing, do we know the current function? Yes, we've got the current scope. Right, so we can, so first thing that we need to do is keep track of the current function. So, so let's keep track of that. let's just add a pointer here. Current function, which is initially null. Okay. And then when we pass a function definition, right here, so we had an open brace, we pass a function definition, we set the current scope, we also setting the current function to our function decker, and then we are setting the current function back to null. Since we can't nest function definition, we don't need to worry about that. Okay, so now when we pass a return statement, we can check that the type matches. So we want to return a return statement. So we get the state, we get a position, and we get an expression. And we want to create a return statement. Like so. But we also want to check that the type match. So the type of the expression must match the return type of the function. Of course, we can also have an implicit conversion in actual C. So let's add a to-do, support implicit conversions here. And since the type are interned, we can just compare pointers. However, we want to know whether the types don't match, and if they don't match, then we want to create an error. So state logger log incompatible return type. Let's just say that. This is CNO. And then the primary diagnostic is at the position where we have the return statement. Return value let's just say return finish and see how it looks. Okay, so incompatible return type. Where are we returning? Interesting. So this should be the same type. Oh, I see. I can't actually compare them by pointers. That is so. The types are interned, so there is only one int type. But this int type here is part of the return type of a function, whereas the type of the variable n is the standalone int type. And those need to be different because we're using intrinsically linked list. So I can't actually compare them by pointer. So I need to manually write something like is the same type. Okay, so that is the first issue. And then the diagnostic also doesn't look nice. Okay, but let's fix the correctness one first. So we need to write a function that compares two types. So is same. Probably need to would have needed that at some point anyway, because of type depths, right, and things like that. So potentially, okay. So if we have the same one, then it's true. Otherwise, that is, I can do a bit of a hack here, because for the hash table, I already specified equality, so that it knows how to hash them. And then I've got an isEqual base function that I can call. and it will do the correct logic here. Okay, and why does this definition not match? I haven't saved it. Okay, so then in the compiler, I call so if the types aren't the same, then we issue an error. Right, and now we're only having one here. But this isn't entirely nice, so let's first of all capture the entire thing. So then I can do the location is the entire keyword. Or rather, okay, so now we highlight the entire return statement as the point of the error, but actually the error is the expression that we're returning and not the return itself. So let's do that instead. Because I can just query location of the expression, I believe. That one's also ugly. Okay, let's fix that later. So we've got the location of the return type, but we also got the annotation where the return type is declared, which is the function. Return type declared here. Expression returned here. And no semicolon. Okay. So now we mark the, right, we don't directly mark the void here, which would be like the ideal location where we specify the return type, but I don't have that sort of fine-grained location information in the ST. But that seems acceptable for now, and we need to fix the location for expressions later. Okay. I believe that error message is acceptable for now. Incompatible returned incompatible type of returned expression and return type of function. Let's be a bit more precise. Yeah, okay. That one's fine. So the second thing we are not allowed to do is that. However, we will happily declare a variable of type void, and then also allocate 64 bits of storage for it. I mean, this is fine, right? It doesn't hurt anybody, but we should probably still catch that. And so the standard actually check that types are partitioned into object types and function types. So variables only have object types, and this is ensured purely syntactically. However, an object type may be incomplete, and when we have an incomplete type, it can only be used when the size of an object is not needed. And when we create a variable, the size is needed, so it cannot be incomplete. And then a couple of pages down, it says void type is an incomplete object type. So let's prevent incomplete object types for variables. For now, I will just add a function is complete. We probably would need to change that at some point, because whether or not a type is complete this can change throughout the program, right? So when you just declare a struct, it is incomplete, but then when you later define it, it is complete. So this simple predicate probably doesn't work once we go there, but since we don't have structs, it is fine. And then we say if the type, so if we have a function type, then it is not a complete. So maybe is complete object type is a better term. So is complete object type. Functions cannot be complete object type, and otherwise it must not be void. And then we adjust that later on. So now when we create a declaration, right here we create a new variable decl. We want to ensure that its type is complete. So if we don't have, then we want to issue an error. So we want to create an error message. Invalid use of incomplete object type. Primary annotation is at the location where we declare the name, used to declare variable here. Okay, so invalid use of incomplete object type used to declare variable here. Okay, so that one's an error. What happens if we use it here? Okay. Wait, what? Oh, that is interesting. So the error is now complaining that it's perfectly fine having a parameter of type void, but it's not fine that we then return it of type void in a function that returns it. It should complain that the parameter is void instead. So where do we define parameters? Right here. We also need to do a similar check for parameters. Used to declare parameter. Okay. So now we are getting an error that we've got a parameter of type void, and then we're getting a second error that we're returning an object of type void for a function that returns it. But that is fine, I think. Yeah. So what we don't get an error for is that we are then doing arithmetic on void. We will tackle that later on, because then we would also need to do like checking for conversions. So let's just keep it for now and say we've implemented void. We can return void from a function, and if we use void in any other place, we will not allow it. Okay. Okay, so we've added void. This means that we should then probably also allow this form of return statement. So return without an expression for a void function. So when we go to our return statement, expression can be null, I'm assuming. Let's just see what happens. So when we go to the compiler, and we pass a return statement, we either pass a semicolon or we are passing an expression followed by a semicolon. Okay, so that means we need another overload. This can only be used if the function returns void. Otherwise we issue an error. Let's copy this message and adjust. Function returning non-void must have a return value. Function with non-void return type. Return type declared here. And then missing expression here. Missing return value here. Otherwise, we create a return statement without a corresponding expression, which means that we need another constructor that does not take an expression. And I wonder what happens during codegen. It seemed to handle it just fine, which is interesting. I expected some sort of crash. So what do we do during codegen for a return statement? We simply generate a return. Okay, so that is fine. Okay, so that was very much straightforward. So now we can check that it actually returns something. So now this prints nothing, and when we return here in main, we get an error. Okay, and this Unicode, this is part of NeoVM's terminal emulation and not my output. Okay. Okay, so that was void. Let's add more interesting types by going looking at more integers. So I want to add more integer types. Let's in what order should we do it? So currently we're having the type int, and since we can pick since C does not require that int has a specific type, we chose int to be 64-bit, because loaf is a 64-bit interpreter, and that's the native integer type. This means that when we want to do like long int and short int, so first of all, what should be the size of long int? Long int, right, I mean, int is already 64 bits, so it would make sense to have like long int mean 128 bits or something, right? That would be useful. However, loaf doesn't support that big integers at the moment, so we can't do that. The more interesting thing is what about short int? So short int can either be 16-bit or 32-bit. And whatever we pick, we then don't have any way to express the type that we didn't. So if short int is 32-bit, we don't have any way to do like a 16-bit integer. Because like it's not really. So let's say we're having let's say short means 32-bit. And then we can allow it as an extension a short, which means 16-bit. Okay, so and then we're having char, which is an 8-bit type. Okay, and then we're also having like the signed and unsigned versions. So let's first of all rename this one from int to sint 64. Okay, because this is a signed 64-bit integer. And then let's just add the uint version first. Okay, so now we're having a signed 64-bit integer and an unsigned 64-bit integer. Which means that we need to adjust the printing code. So let's say this is int 64. Signed int 64 and uint 64. Okay, we're not printing the types in any form of C syntax anyway, so let's just be clear names here. Okay, and then the parsing stuff gets interesting. So when we pass a declaration, we are parsing a bunch of specifiers followed by a declarator. And specifiers can be storage class, type specifiers, or functions. And type specifiers is essentially a collection of those keywords. They can occur multiple times in the expression, like long, or int. Long. So they can occur multiple times. They can occur in any order. So we can do like int long, long int long, or something. So we simply have like a collection of type specifiers. And then the standard specifies which which combinations are allowed and which ones aren't. So what we are currently doing is we're simply parsing in the compiler. When we're parsing a type specifier, we're simply parsing one keyword, like either an int or a void. But we need to parse like a collection of all of those keywords. So instead of having the type specifier return a type, the type node itself, we need to create like a collection of those specifiers. I mean, we can return we need to parse a collection of keywords. Okay. So for that, let's just say that instead of calling this built-in types, let's call it keyboard type specifiers. And we're having void, int, and then let's add signed first, which is like the most useless. Well, it's not useless because of signed char, but like signed. Let's add the keyword signed. What value does it produce, right? It's not a built-in type kind. So we need to add like an enum for type specifiers. Okay, so let's add an enum for the type specifiers. Type specifier. Void, int, signed. It's annoying that they're all keywords. Okay, and then we're returning, this one returns a type specifier. Type specifier void, type specifier int, type specifier signed. Okay. And then when we pass a type specifier, we are passing a list of symbols, type specifiers, and then we collect them all in a vector. So then we're getting a vector of type specifiers. Okay, and then we need to essentially look through this list, essentially need to match the collection of type specifier that we just passed with this list of allowed combinations of type specifiers. Yet, this is going to be a lot of annoying ifs. Okay. So what can we have? We can have like a base type. Right, so we can have like an int somewhere, and then we have an integer type. Or we have a void, and then we have a void integer type. And I'm assuming the default, because if you just do signed, is probably allowed. Yeah, if you just have signed, we have an int. So the default base type, let's say, is int. Built-in type base type. I can use auto. So we begin, the default is assigned int 64. And then we iterate over the specifier. And then we do a big switch over the specifier. Okay, if it's void, we change the base type to void. If it's int, we do nothing, because we already have the correct base type. And if it's signed, let's say signed is true. Is signed, and since signed is the default, we initialize it to true. And so is signed. Okay. So then we need to do checking. So if we're having a void specifier, so let's keep track, have base type. Base type. If we already have a base type and we specify void, so we're having something like int void in one, so int void, right? Then we already had a base type, the int, and then we have another one, so this is an error. Similarly here, we are setting, and if we already have a base type, then this is an error. Okay, if we're having the type specifier signed and the base type is void, this is also an error because we can't have a signed void. Okay, let's generate the error messages later on. But for now, I believe that is all the error messages that we could reasonably have. Let's convert now all of that information to an actual type. So we switch the base type. If it's void, it's easy, we always return void. If it's signed in 64, and it's signed, then we return signed in 64, otherwise we return the unsigned version, and we will never reach this point because UN64 is not a base type. It's only created by modifiers. I believe I have unreachable, not a base type. And then a return null type. Okay. So now. Okay. This shouldn't have changed anything. Because we are still not doing. Okay. So let's directly add unsigned. So where do I specify signed? Let's also add unsigned. 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 So base types, modifiers. And then when we pass a type specifier, we can have unsigned. We cannot have an unsigned void, and it's reset is signed to false. Now we can have another issue, which is multiple signed, unsigned within one declaration. So sign modifier count is initially 0. And then we increment it. I don't need a count, I can just need a boolean. And let's actually make this nicer by using optional. So the base type, built-in type, type kind t, base type. And then we also have assignedness. And then I don't need these separate booleans. So if we're having a base type, signed in 64. And then set is sent to true, set is sent here. We're now doing value or. If we then have a base type, we are using signed x64 as the default. Right. And if is signed value or true, so the default for signed is true, we do it like so. Okay. And now we can pass unsigned. What I wanted to do was check that we, if is signed, let's be a bit more explicit here, because we have an optional of a boolean, and then the implicit boolean conversion is always a bit annoying because we don't know whether, right? So if is signed has value, then this is an error. A lot of annoying checks. Okay, because we can't have unsigned and signed, right, multiple times. And yeah. So now when I go into the test, I should be able to do something like unsigned int, and it should at the very least pass. But since we don't have implicit conversions, a lot of things are going to break. Actually, right. Since we're not, so the type of the variable is now un64, but the type of the integer literal is still assigned in 64. But since we're not doing any type checking whatsoever, nobody's complaining. So that's obviously not ideal. So let's also add unsigned, like the suffix for the integer constant. So we can have an unsigned integer conversion. So where do we have those? Somewhere here in the grammar. We've got constants, and then an integer constant has an integer suffix, and an integer suffix has an unsigned suffix. And this is the only one that we care about, so u, basically. So when we pass an integer constant expression, we've got suffix, suffixes, which is a symbol table that returns suffix, which is an enum that we need to define. So enum suffix none unsigned. And then we've got, I think, the map u maps to suffix unsigned, capital U maps to suffix unsigned. And then after all those digits, we have an optional suffix. Which means that right here, now we're getting an optional suffix. If the suffix, let's s, the suffix is unsigned, then we want to have an un64. Otherwise, signed in 64. Okay. And now we should specify like a suffix right here. And now everything has type UN64 in our AST. Okay, but in the bytecode, we are still doing assigned comparison and assigned subtraction and assigned addition. So we need to teach CodeGen about unsigned. Right. So this is right here, where we do essentially create the arithmetic built-ins. We need to switch to the unsigned version if necessary. So we also need the type. Right. And this is the point where we need to look at the, for example, like addition is defined for integers and floating points and pointers and things like that. So let's take a quick look at the standard. Expression, addition, arithmetic type, and pointer and integer. Okay. So and arithmetic types, I'm assuming they are like floating pointers and integer types. There are, where does it say? And complex types. I'm guessing, where do we have arithmetic? Oh yeah, integer and floating types. Yeah, and okay, that's okay. So arithmetic types. So here we need to determine, like if we have a signed integer, then we're doing that. If we have an unsigned, and also if we have a float. So if we're having a signed int, otherwise if we're having an unsigned int, then we're doing that. Invalid type. Right? Something like that. Okay, so let's define the corresponding predicates. So void signed int, unsigned int, signed int, unsigned int. And then here during the CodeGen, we just need to repeat the same pattern for subtraction. Multiplication. Division. Reminder. Right. Unsigned division actually can't overflow. Signed division can only overflow because int min divided by -1 is an overflow. And remainder can never overflow. It does have undefined behavior in C because we cannot do int min modulo -1 because the corresponding division would overflow and it's usually mapped to a single instruction that does division and modulo at the same time. So in C, int min modulo -1 is undefined behavior. But in Lauf, the implementation catches that. So we don't have UB there. Instead, it just does the right thing. Okay, that's just on the side. Bitwise operations are the same, except for shift. So if we're having a signed int, then we're doing an arithmetic right shift. Otherwise, if we're having an unsigned int, then we're doing an unsigned right shift. Okay, And that is the operations. Of course, we want the type of the expression. And at this point, like CodeGen assumes that we inserted implicit conversions if necessary, and that for an arithmetic expression, the return type is the same, right? Is the type that is necessary for the type switching. So we're assuming that like signature T and returns the T. So this is the type that we're passing. And we're calling it another time here. So now we're doing unsigned operations, but we're not need to handle comparison because we're still doing a signed comparison. So when we do, let's just look for call built-in outside this function for print, and here this is fine. Negation does a signed multiplication, but I believe this is fine because I don't know what happens when you actually do like unary minus on an unsigned. Not is a bit operation, same for logical, so this doesn't matter. And then here comparison is signed in. We're handling a signed integer, and then we're doing a signed comparison. Then we're doing an unsigned comparison. Otherwise, we're having an invalid type. Okay. And now we're properly handling unsigned integer types, and they're still generating a signed comparison. Why? Where do we do the comparison? So right here we're doing. Why is that type is so we say that the return type of the comparison expression, that is okay, that is interesting. So the return type of the comparison expression is signed x64 because the C standard. How do I get out of this search mode? Get me my outline back. The C standard says that C doesn't have a Boolean type. Well, now it does, but like the early C doesn't have a Boolean type. So equality operations result has type int. So the return type of a comparison expression is an int. And we're using that to determine which comparison to call. Like the type of expressioner type, that is the type of evaluating the expression, which is always int. What we instead want is the type of any operand. And since we are assuming they are the same at this point, we can just pick the left one. Right, and now we're getting a correct. We're doing an unsigned comparison. Great. Let's commit that. At unsigned integer type. Now the question is, there's still time in the stream. Should we tackle like proper type checking? So what we're currently doing is when we create an arithmetic expression, we're simply copying the type over at the left and assuming that both operands have the same type. We should generate so we should definitely do type checking and generate a proper error message. But what we should do first is handle all those errors right here. Right? For all the combinations of invalid modifiers, we should generate an error message. And I'm a bit lazy at this point. Like here, the error would be something like conflicting base type specifier or something, right? Because we have like an int void or something. And here the error message would be like duplicate signed modifier or something. but I'm a bit lazy. And like the goal is to do like actual code generation and not like generate the best error messages for a compiler. So let's just say that whenever we have this error, we just generate an invalid combination of type specifiers and have the programmer figure out what the actual cause is. So let's just pass a position for our error message, and then we write log error function that simply goes ahead and logs an error message. Invalid combination of type specifiers. Rotation kind primary, position here. Right. It's not the nicest error message, but it will do. And then the 9 took it. Okay. And now when we modify the code to do like an unsigned int signed, we're having an assertion failure. Because we need to use that syntax. Right, and then we're getting an invalid combination of type specifiers. Right. And then just as, right, that's good enough, I think. Interestingly, like the last one takes precedence, so this is now considered a signed integer, and then we get an error here. And like ideally, this error message would also say that the return type is unsigned int and the expression has type signed int, but that is fine. Let's just throw in a void in there for good measure. And then we're getting the same error multiple times. It's treated as a void, so yeah. I believe that is good enough. Let's just amend the previous one. Okay. So now the question is, so we've been streaming for an hour. What can we do? So either we can do type checking. Let's, instead of doing, so we should definitely do something because CodeGen assumes that both operands have the same type. So let's just say that they need to have the same type, otherwise we have an error. So let's write a function. Let's just do type checking. Very basic type checking without implicit conversion and just asserting that the types have to match exactly. And then later on we figure out how to do like implicit conversions. So function call. We're checking that we are calling a function. So that's good. Then we're checking that the parameters and argument matches, so that we haven't missed any arguments. And then next up, we just need to iterate over them and check that each type matches. Let's do that. Equal this version. Parameters and arguments begin, arguments end. Actually, I don't want equal, so I want to check that all types match, but I don't want to get a single Boolean result. I want to generate an error, so I want to do like, is there like a simple just iterate like a zip algorithm? I mean, I can do something with my algorithm knowledge isn't good enough for that. So I want to, like, I want a lambda, I want to have it invoked for every pair of things. There's like an adjacent Like I can mismatch some form of adjacent something to do that. Let me check. Yeah, I can mismatch adjacent difference. No, not adjacent different. Like, not that one. Okay, let's just do the comparison and then just say some type this didn't match, and that's fine. Because like you can spend ages generating good error messages, but like that's not really the point of this project. So we're getting a parameter type and an argument. So we're getting param type, and then we're getting an expression which is the argument. And then I want to return the same, the parameter type, and the type of the argument. And if they're not the same, then we issue an error. Mismatched parameter and argument type. Primary annotation, which is, so the primary annotation is the location of the call. And then we've got a secondary annotation, which is the location of the function definition. Function here. Right, we want the location of the name of the function here for the call, and then here I want the declaration of the, I don't actually have that one easily available. I don't like the function isn't the function declaration. It's an expression that evaluates to a function, which can be something like an operator, like an array index in principle. So there's no easy way to get from there to a declaration of a function. So let's do that. And let's actually have a mismatch. Right? So mismatch parameter and argument type. And like, yeah. Error message could be nicer. And since we're doing like equal anyway, we don't need to check the parameter count, because the version that takes 2 ranges does that for us. Okay. So that's type checking of function calls. To do allow implicit conversion. Okay. So here we need to do a type check that the unary operation is allowed on that sort of type. So let's see, maybe that's easy. So we've got plus, negation, bitwise not, and logical not. Unary operators. Unary arithmetic operators. Plus or minus one's arithmetic type. This one's an integer type, and this is scalar type. Okay. So let's add queries for those. So bool is arithmetic. Is integer. Is scalar. So is integer, it's very easy. That one's just signed int or unsigned int. Arithmetic is currently also integer. I just noticed a comment in the chat about 0 arguments. We're handling 0 arguments because then we're having an empty range and like we're checking the size. So a stood equal checks the size for us. And scalar is also arithmetic. Yeah, okay. So we are switching over the operand. So if we have a plus or minus, we want, what did it say? Arithmetic type. Not so the operand should have arithmetic type. Let's say is valid type. Just immediately invoke lambda. So here we want arithmetic type. Here I want integer. And here I want scalar. Okay. And if we don't have a valid type, we issue an error. Copy this one. Invalid type for a unary operator. Up.log. Okay. And again, like a nice error message would say what the type is and so on, but we're not doing nice error messages. So the result of the plus operator is does integer promotion. We don't do integer promotion, so that's fine. Minus also does integer promotion. This one also does integer promotion. And this one is always int. Okay, I can do the last one. So if the operator is L0, then I want the built-in type int, which is SN64. Otherwise, I want the promoted type. To do promote type. Okay. Arithmetic conversion, let's just check that the types are the same. And like arithmetic type, yeah, let's check for arithmetic types here. I believe for all kinds of operators, like except like those ones allow on all arithmetic types, and then we can do addition and subtraction on pointer and integer. We don't have pointers, so don't worry about those. And then these ones all require integer types. I'm not bothering. Let's take care of that later and just assert that the types are the same. Is same left type, right type, and actually like generate the correct error message already. Cannot do implicit conversion between operands. Okay, and then actually to do conversion. And I guess, okay, let's check, do the same thing over here. It's not that hard actually. can you please generate switch for me? Okay, does not want to. So I have to do like fancy search and replace, like so. And here I want arithmetic type on the left, because they have the same type. And here I want integer type on the left. And here I actually want arithmetic op that. Okay, invalid type for binary operator. And that's that. Right, I'm just checking whether the tests still pass. I'm not checking for the error messages. Comparison. Like have real, oh, right. We want a real type because C has complex types. Of compatible, like pointers. Like what's a real type? I'm guessing it's an arithmetic type that isn't complex. I would just, right? Yeah. Okay, let's just say comparison is allowed between object types. And same deal. So we want the same type and we want arithmetic types. Cannot do an implicit conversion. And we want arithmetic type. We will probably not implement complex types anyway, because why would we? So that's fine. So we can compare arithmetic types. Sequenced in this case means and or like the version of short circuiting. This one, scalar type. And the result type has type int. So we're already doing return type int, and we want scalar type. So this one, and we want scalar. Invalid type for logical operator. And then finally, assignment. Let's just check same type again. Do we assignment shall have a modifiable L value as its left operand. So no type specified. Right. A bunch of type specifiers, so let's not bother checking those. To do type check, and then finally we've got the last one, which is the ternary operator. First I want a scalar type, and then we need like the common type logic for the first one. So let's just check that the first one is scalar. Is scalar addition invalid type for ternary condition, and then checking that the other ones are the same. If true, if false, and right, that should be it. So now we're doing very basic type checking of expressions. Right, and we are getting a bunch of errors. So invalid type for comparison. What do we check for comparison? Left and right comparison. They should be the same and they should be arithmetic. Why is that not the case? Let's debug our example because we've got the same error here. Right, there's no way to figure out what the type is and the debugger is there. Okay, this would be useful to actually now get the type in the diagnostic message. What do we say? Arithmetic means is integer. Let's hide this error message temporarily and see what. Oh, no, I don't think this is related. So we do a comparison. These are all UN64s. And UN64 is should be unsigned. Okay, let's step in here again. So, is signed int. It's a UN64. So unsigned int should return true. It helps if we negate the, yep, someone in chat pointed that out, thank you. Negate the condition. If you don't want. Okay. And I'm probably having the same one right here, yep. Not scalar. And then we're probably doing this right here, not scalar. Okay, so that works now. And as we can always see, if we do things like forget the -1 here, we're getting an error message. Right? Cannot do implicit conversion between operands. And the again, this messed up. This probably points here. The annotation. Okay, I believe that is good for now for like early checking. Of course, we do need to add implicit conversion. Add basic type checking of expressions. But that's it for the stream. We made good progress. So I won't be streaming on Thursday again, so we'll be streaming next week again, where we'll either add more integer types like short ints or long ints or something, or look at adding conversions. I have to see what's easier to do first. So thanks for stopping by. Hope you enjoyed the stream, and until next week.